Okay, so we're going to go over the 2.6 and 2.7 handouts. So I'm going to go ahead and share my screen here. Okay. So in 2.6, we talk about what are called rational functions. So a rational function is one where we have a polynomial in the numerator and denominator. Remember that a polynomial has only nice powers of x, like x to the first, x squared, and so on and so forth. So we have those on the top and we have those on the bottom. Now, rational functions have strange behavior, unlike the polynomial functions. Like the domain of these functions is not all real numbers in general. Now, we have to worry about where is the denominator equal to 0. And so there's a few cases we think about. Like in one case, you could have that the degree on top is less than the degree on bottom. You could have that the degrees on top are the same, or you could have that the degree on top is bigger than the degree on bottom. So we're going to explore these cases as we go through this handout. So as an example, like if we had the function x plus 3 over x squared plus x minus 2. So there's two numbers that would make x squared plus x minus 2 equal to 0 if we plugged in -2 or if we plugged in 1. So the domain of this function would be everything except those two numbers, -2 and 1. But like we can get really close to -2 and 1 and not have any problems. So what happens as we get closer and closer to those bad numbers? Well, as we get close to -2 from the left side of -2, we see that the y's are getting very large. As we get close to -2 from the right side of -2, we see that the y's are getting very large in the negative direction. So as we approach -2 from the left side, the y coordinates are going up. But as we approach -2 from the right side, the y's are going down. Now, the other bad number is 1. That would make the denominator 0 as well. As x gets closer to 1 from the left side, the y's are getting large in magnitude in the negative direction. As we approach x equals 1 from the right side, the y's are getting large in magnitude in the positive direction. So what happens as we get close to the zeros of the denominator is generally that the y coordinates get very large in one direction or another. So we can also ask, just like we asked with polynomials, what happens on the ends of the graph, on the extreme ends, like the left end and the right end? So let's imagine we ask such a question as we go off to the left end of the x-axis. So as x becomes very large negatively, if we plug in these very large x's to our function, what we see happening is that the y's are getting very close to 0. If we plug in very large positive x's, we see that again, the y's are getting very close to 0. So the end behavior of this graph is that the y's will tend to get very close to 0. Okay, so kind of summarizing all this behavior as we go on to the next page. Okay, so we can sort of get a crude picture of this graph. So we have these bad numbers at -2 and 1. So I'm going to kind of just make some dotted lines here to represent those. Now, we said on the previous page that as we approached x equals -2 from the left side, our y's were getting very large. And so I have something like this happening as I come at -2 from the left side of -2. As we approach -2 from the right side, we saw that the y's were getting very small. In other words, what we see happening is behavior like this. as we come at -2 from the right side. For that other bad number 1, we saw that as x got close to 1 from the left side of 1, the y's got very small. So we see something like this. And we saw that as we approached x equals 1 from the right side, the y's got very large. So as we approach x equals 1 from the right side, the y's become very large. Now we could plot some points in the middle just to kind of fill in the missing pieces here. Ultimately, this kind of looks like this. This one takes a little dip into negative territory and then gets closer and closer to 0 as time goes on. So we get these strange looking graphs when we have these so-called rational functions because they have some problem numbers, those numbers that make the denominator 0. The lines x equals -2, and 1 are called vertical asymptotes. So these are the vertical asymptotes. And in this case, the line y equals 0, which is the x-axis, is called a horizontal asymptote of the function. So horizontal asymptote is the horizontal asymptotes are the end behavior of a rational function. They represent the number that the function approaches as time goes on. It is possible that we don't approach just some number, as we'll see later. But in summary, so we looked at the case here where the degree on top was less than the degree on bottom. The degree on top is 1, the degree on bottom is 2. When this happens, assuming that the fraction is in lowest terms, and we'll see when it's not, what happens when it's not later, the vertical asymptotes are the zeros of the denominator. The horizontal asymptote is y equals 0. So looking at a concrete example, we're going to graph f of x is x minus 4 over x squared minus x minus 6. So first we check that it's in lowest terms. Meaning, is there anything that can cancel out, any common factors? Well, x squared minus x minus 6 can be written as x2 times x minus 3. So it's not going to cancel out with x minus 4. And excuse me, I didn't really write where that came from. So the denominator, x squared minus x minus 6, is x plus 2 times x minus 3. And so we see that there's no x minus 4 to match the top. And so this thing is in lowest terms. Okay, so the next thing we see, the next thing we do is we start finding the vertical and horizontal asymptotes. So the vertical asymptotes, we'll just abbreviate those as VAs. These are the zeros of the denominator. So x squared minus x minus 6 equals 0. Now we did already factor this to check that nothing canceled on top. So this is x plus 2 times x minus 3 equals 0. And therefore x is -2 and x is 3. So these are our vertical asymptotes. Next, we check the horizontal asymptote. Well, we note here that the degree of the top is less than the degree of the bottom. When this happens, the horizontal asymptote is y equals 0. This is automatic. If the degree on top is less than the degree on bottom, if you plug in very large x's in either the positive or negative direction, you're going to get y's that are very close to 0. Next thing we look for are intercepts. So let's see if there's any x-intercepts here. So x-intercepts are found by letting y equal 0. In other words, letting x minus 4 over x squared minus x minus 6 equals 0. Because this is the formula for the y coordinates. But the only way a fraction can equal 0 is if the top itself is 0. So we must have x minus 4 equals 0 or x equals 4. So that's our x-intercept. All right, so next we will look for a y-intercept. Okay, so our y-intercept, we just let x be 0. So this would be f of 0. That's 0 minus 4 over 0 squared minus 0 minus 6. And so as you can see, what's left over is negative 4 over negative 6. In other words, 2/3. Sorry. Okay. So the last thing we check for is potential symmetry. It's pretty unusual that these will have symmetry, like most of the problems won't. But if it does have symmetry, then if we know what's happening on the right side of the graph, we know what's happening on the left. Now we can say very quickly that this one is a no, because x equals negative 4 is not also an x-intercept. Like if I have information about what happens on x equals 4, the same sort of thing should be happening. Really the same thing or its opposite should be happening on the other side of the y-axis, and we don't have anything about negative 4. Okay. Like here, if I plug in x equals 4, f of x is going to be 0. If there were symmetry, then f of negative 4 would also be 0. So no symmetry. All right, so let's start drawing what we can from the information we have. We have vertical asymptotes at negative 2 and 3. Horizontal asymptote is y equals 0, which we've already sketched. That's the x-axis. We have an x-intercept of 4. And we have a y-intercept of 2/3. Now, we need a little more information. We have no idea what's going on the left side of this asymptote. We don't know, like, are we going toward this asymptote this way? Are we going toward this asymptote this way? I would say we know for sure we're going toward this asymptote going up, because if we were going down, we would cross the x-axis, and we already found our single x-intercept. And we don't know, like, are we going up this way toward this asymptote, down this way toward this asymptote? So we need to find out some things. To do this, we simply plot some points. And I can just do this in a calculator, but like, let's find something on the left side of the asymptote, like negative 3. Let's find something on, like I said, I already know I kind of know, like, this must be going like this, because if this tail were pointing down, then it would cross the x-axis. And again, we already know everywhere where we cross the x-axis. So this is pretty much the only thing I know. But I don't know, does it go down like this or up like this as we approach negative 2? So let's pick like negative 1 to see what's going on right here. And then we don't know, do we get close to the asymptote going up or going down? Now there's no nice numbers between 3 and 4. So I'm just going to have to pick like 3.5 or 3.5. Okay. If I put these in my calculator, I get negative 7/6 when I plug in negative 3. And if I plug in negative 1, that would give me 5/4. And if I plug in 3.5, it gives me negative 2/11. And you might get some decimal in your calculator instead of negative 7/6 or negative 2/11. That's perfectly fine. Really, I'm not interested in the exact y's as much as I am about where are they with respect to this horizontal asymptote. So like 2 of them are below 0, 1 of them's above. That's what I really care about. So at negative 3, I'm a little bit below negative 1. Now, this is a point that's below my horizontal asymptote and left of my vertical asymptote. So I'm going to sketch something that sort of keeps that trend going, which puts me here. At -1, I'm at 5/4, which is a little bit above 1. So I have something like this. I must be headed upward as I approach this asymptote. At 3.5, I get -2/11. So just a little bit below 0. This is a point that's below the horizontal asymptote and to the right of the vertical. So I'll just sketch a graph that continues that trend. Now I do go above the x-axis perhaps temporarily, but as time goes on, I'm going to get closer and closer to it, to y = 0. Okay. So I want to look at another example now. Let's consider the case where the degree of the top and the degree of the bottom are the same number. So we're going to accept that the vertical asymptotes, as long as you're in lowest terms, the vertical asymptotes are the zeros of the denominator. So like this one would have vertical asymptotes at -3/2. That's where the denominator is 0. But let's ask what happens on the extreme ends as we go off to the left and right ends. If I plug in very large negative numbers into x, so that's the left side of the graph, I see that my y's are getting close to 2.5. Also, if I plug in very large x's in the positive direction, I see again that my y's are getting close to 2.5. So as x approaches both -infinity and infinity, in other words, as we go off to the extreme left and right ends of the graph, the y values are approaching 2.5. And what do you know? That's 5/2. Okay. So if we have some rational function where the degree of the top and bottom are the same, note that these both have degree 1, then the vertical asymptotes, assuming we're in lowest terms, are the zeros of the denominator, and the horizontal asymptote is the ratio of the leading numbers. Okay, so if A is the front number on top, B is the front number on bottom, then the horizontal asymptote is A over B. So like in this case, where we have 3x over x minus 1, let's again get a graph of this rational function. Just trying to bring a little more light in here. Okay. So let's graph this function, 3x over x minus 1. And so first, we're going to note that it's in lowest terms. I mean, both factors on top and bottom are prime. I'm not going to factor 3x down any further. I'm not going to factor x minus 1 down any further. And so anyway, so the next thing I'll do is find asymptotes and all that. So vertical asymptote, these are found by setting the denominator to 0. In this case, that'd be x minus 1 equals 0. So x equals 1. As far as a horizontal asymptote goes, since the degrees on top and bottom are the same, they're both x to the first, we simply take the ratio of the leading numbers. So 3 over 1. In other words, y equals 3. We next seek out any intercepts. This is done by setting the function equal to 0. Now, a fraction can't be 0 unless the top is 0. So we must have 3x equals 0. In other words, our x-intercept is x equals 0. Next, let's find the y-intercept. Here we'll let x be 0. f of 0 is 3 times 0 over 0 minus 1. So that's 0 over negative 1, or 0. We next ask, is there any symmetry? Now, in the last example, we said, well, x equals 4 is an x-intercept, but x equals negative 4 isn't an x-intercept, so the answer is no, and we knew that explicitly. Here, I could say, well, I have a vertical asymptote at x equals 1, but I don't have one at x equals negative 1. So vertical asymptote at x equals 1, but not x equals negative 1. Because of this, no symmetry. All right, so let's sketch the graph the best we can. So I've got a vertical asymptote at x equals 1. I have a horizontal asymptote at y equals 3. I have an x-intercept and a y-intercept, of course, at 0, and no symmetry. So I don't know anything that's going on the right side of my vertical asymptote, but I see a point on the left side. It's below the horizontal asymptote and left of the vertical asymptote. So we're going to draw a graph that continues that trend. So there's the left side of our vertical asymptote. To find out what's going on the right side, just pick a number on the right side, like x equals 2. So let's put 2 into our function. On top, you'd have 3 times 2, which is 6. On bottom, you'd have 2 minus 1, which is 1. So when x is 2, y is 6. So we get a point way up here. This point is to the right of the vertical asymptote and above the horizontal asymptote. So we'll just sketch a graph that continues that trend. And now we have the graph of 3x over x minus 1. Okay, so the next case we're going to look at is the case where we have the degree on top is greater than the degree on bottom. Now, if we have x squared minus x plus 3 over x plus 2, we can do division. I mean, x goes into x squared. So if we were to do the synthetic division for this, like go through the process of doing that, we would see that we have x minus 3 plus 9 over x plus 2. Okay, so that's just me doing synthetic division, like negative 2 in the little box, because that's like x minus negative 2. And then doing 1, negative 1, and 3, and doing the synthetic division. This is the result we get. So if we explore the end behavior of the graph, like what's going on the extreme ends, if I plug in large negative x's, so the extreme left side of the graph, I see that I get large negative y's. But there is a easy to understand pattern. You have negative 1,000, then negative 1,003, and some minimal change. Plug in negative 10,000, you get negative 10,003 and some minimal change. Plug in negative 100,000, you get negative 100,003 and some minimal change. In other words, you plug in x, you get x minus 3, and then something that's barely there. See, if x is really large, then 9 over x plus 2 is going to be almost 0. Like if x is a trillion, you get 9 over a trillion 2, which is, almost 0. So if we plug in very large positive x's, if x is 1,000, y is 997 point something. If x is 10,000, y is 9,997 and something negligible. If x is 100,000, y is 99,997 and something minimal. So what's happening is, again, we plug in a large x and we get essentially x minus 3 for y. That's what's happening here. When the x's are really large, this fraction is basically 0. It contributes something only very small. So on the extreme ends, plugging a number into f is effectively the same as plugging said number into g of x equals x minus 3. So the ends of the graph of f look nearly identical to the line y equals x minus 3. And in this case, we call that line an oblique asymptote of f. So in this case, there is no horizontal asymptote. We're not approaching some number. That's what represents a horizontal asymptote. So in general, if you have the degree on top is bigger than the degree on bottom, still assuming it's in lowest terms, the vertical asymptotes are the zeros of the denominator. The oblique asymptote is what you get for the quotient when you divide the top by the bottom. So it says g of x is the quotient. So that's the whole part before the remainder. If that quotient has degree 1, we sometimes call that the slant asymptote because it's a slanted line. Like x minus 3 is a slanted line. So as an example, we could graph f of x equals x squared minus x plus 1 over x plus 1. So this thing is in lowest terms. X squared minus x plus 1 is not going to factor. And even if it did, x minus 1 is not one of its factors. I can't think of anything I could multiply by x minus 1 to get x squared minus x plus 1. So since it's in lowest terms, we can go and find the asymptotes first. So for vertical asymptotes, we put x minus 1 equal to 0. And so x equals 1. Since the degree on top is bigger than the degree on bottom, we're going to have an oblique asymptote, which I'll notate by OA. The way this is found is synthetic division. X minus 1, so I'll put a 1 in the box. Then on top, I have a 1x squared, a negative 1x, and a positive 1 on the end. Now I'll run this through synthetic division. And so an alternative way to write f of x, which is the quotient of these two, is x, because you have the quotient has a 0 constant and a 1 in front of x. And then you have that remainder of 1. The whole part of the quotient is the oblique asymptote. So the part before the remainder, that's the oblique asymptote. And what this tells us is that our graph is going to look basically like y equals x as it goes off to the extreme left and right ends. The next thing we seek out are any x-intercepts. The only way a fraction can be equal to 0 is if the top is equal to 0. So let's set x squared minus x plus 1 to 0 and see if we can solve it. Now, like we said earlier, it's not going to factor. So we're going to have to use the quadratic formula. So we get x is negative b plus or minus the square root of b squared minus 4ac all over 2a. So that would be negative 1 plus or minus negative 1 squared minus 4 times 1 times 1 all over 2 times 1. So x is 1 plus or minus the square root of negative 3 all over 2. But the square root of negative 3 is an imaginary number. we don't have a problem with that theoretically, but we can't graph it. And that's what our goal is. The x-axis doesn't have any imaginary numbers on it. So we conclude then that there are no x-intercepts. So there don't have to be x-intercepts. There doesn't have to be a y-intercept. If 0 is not in the domain, then there won't be a y-intercept. So let's check. Is there a y-intercept? And there will be. I mean, the only bad number here is x equals 1. So we should be able to plug in y equals 0. So f of 0, we have 0 squared minus 0 plus 1 over 0 minus 1, giving us a y-intercept of 1 over negative 1, which is negative 1. All right, so next we check for any symmetry. We can again say x equals 1 is a vertical asymptote, but x equals negative 1 is not. So there's no symmetry. Now, if x equals negative 1 were a vertical asymptote, that wouldn't guarantee symmetry, but it would at least make a case for checking if there's symmetry. But I can say right away, if something similar isn't happening on the left side as is happening on the right side, then I can forget about symmetry. So now we go to get a graph. So I have a vertical asymptote of x equals 1. And I have an oblique asymptote y equals x. To sketch y equals x, remember it has slope 1, 1x, and y-intercept 0. So if I start at 0, I'll go up 1 and right 1 to get another point. And then I'll create this dotted line. And I do have one point on the graph. I have the y-intercept of negative 1. So this is a point that's to the left of the vertical asymptote and below the oblique asymptote. So I'll just draw a graph that has that property. So that at least tells me what's going on the left side of the vertical asymptote. But we don't know what's going on the right side. So let's plug in a number like x equals 2. Now, you could make the argument that because there's no x-intercepts, I can't be in this region here. I can't be in this region below the oblique asymptote, because if I'm below the oblique asymptote, I'm eventually going to have to go down here and cross the x-axis, and we know we can't. So you could reason that we have to be in this area. But if we want to show that, let's plug in a number. So if I plug in, say, x equals 2, and I put it in, you can just put it in your calculator into this, I'm getting 3. Now, think about this. Since on y equals x, you always go up 1 and over 1, we know that the asymptote y equals x passes through 2, 2, because you went up 1 over 1, up 1 over 1. If we're at 2, 3, then our graph must be above the oblique asymptote. So we're to the right of the vertical asymptote and above the oblique asymptote, meaning we look something like this. And now we have our graph of x squared minus x plus 1 over x minus 1. Okay. Now we cut the last case we look at is a special case where the original fraction is not in lowest terms. So if we have the function x squared minus 5x plus 6 over x minus 2, we would expect that as we approach x equals 2, the y's would go close to infinity or negative infinity. That's what's been happening at vertical asymptotes. But here, if I plug in numbers that are close to 2 from either side of 2, the y's are becoming very close to negative 1. Okay, so instead of blowing up, going to positive or negative infinity, the y's are approaching a number as we get close to the problem number in the denominator. And the reason this is happening is because the fraction is not in lowest terms. I can think of x squared minus 5x plus 6 as x minus 2 over or times x minus 3. So these would cancel. So really, effectively, f of x is the function x minus 3. But at that single number x equals 2, we have a problem. So what you would do is you would graph y equals x minus 3, and then you would just eliminate, you would just basically delete the point where x is 2. We call this a hole. So we get a hole in the graph when x equals 2. Specifically, the hole occurs at 2, -1. Y is approaching -1 as x gets close to 2. So if we were to graph this thing, so the function x squared minus 5x plus 6 over x minus 2 is effectively y equals x minus 3. So it has y-intercept -3. And we know that it passes through 2, -1. It's just that there's a hole at that point. 2, -1 was a 0 of the denominator. So we have a hole at that point where the denominator was 0 before cancellation. Now, once the function is put in lowest terms and the hole is addressed, the process for graphing is the same as all the examples we've done so far. So as an example, let's graph f of x is x minus 3 over x squared minus 9. This thing is not in lowest terms. So we can write x minus 3 over x squared minus 9 as x minus 3 over x minus 3 times x plus 3. And then when we cancel those x minus 3's, we're left with 1 over x plus 3. So we get a hole at x equals 3. So this is the 0 of the canceled factor. Okay. The y coordinate of that hole is 1/6. The 1/6 comes from plugging in 3 to this function after cancellation. So plugging in x equals 3 to 1 over x plus 3. Having a hole is effectively like having a point on the graph, because you're just graphing everywhere around that point and then just punching out that one point. Okay. Now that that's been addressed, we can go about our business as usual. Let's look for vertical asymptotes. This happens when the denominator is 0. So that's x equals -3. As for horizontal asymptotes, the degree on top is 0 because there's no x's on top. The degree on bottom is 1 because it's x to the first. So the degree on top is less than the degree on bottom. And when this happens, we simply get y equals 0. Next, we look for any intercepts. So we set the y equal to 0, and y is equal to 1 over x plus 3. The only way a fraction can be 0 is if the top is 0. So that would require 1 equals 0. And of course, that's not going to happen. So in this case, there are no x-intercepts. Next, we look for any y-intercepts. Y-intercepts are found by letting x equal 0. Remember, our new function after cancellation is 1 over x plus 3. So that would give us 1 over 0 plus 3, or 1/3. Even if we hadn't used the canceled function, if I plugged in x equals 0 here, I would get -3 over -9, which is 1/3. This and this are the same thing. The only difference is that x equals 3, this one can't be used because it makes the denominator 0. We check now for any symmetry. And we can say it doesn't have symmetry because you have a vertical asymptote at -3, but not at +3. So as I said, this having symmetry is kind of unusual. We haven't seen it at all here. And even if it has symmetry, you don't even have to use the fact that it has symmetry. You can just still plug in numbers as needed instead of saying, well, if x equals 5, I know what happens at x equals -5, so I don't need to plug it in. It doesn't matter if you realize that or not. You can just plug numbers in all you want. Okay, so let's use the information we have to sketch a graph. All right, so we found that we have a hole at 3/1/6. And that's going to be kind of hard to draw because 1/6 is so close to 0. So you can just see that hole right on almost on the x-axis. We found a vertical asymptote at -3. We see a horizontal asymptote of 0. That's just the x-axis. There's no x-intercepts, but 1/3 is a y-intercept. So, maybe somewhere around here. So really, we know the behavior on the right side of the vertical asymptote. We're above the horizontal asymptote, and of course, to the right of the vertical. So let's make something that's always above the horizontal asymptote and above or to the right of the vertical asymptote. So maybe something like this. So note that this is our hole at 3/1/6. We don't know what's happening on the left side, but I can always plug in, say, -4 and find out. So if I put in x equals -4, that gives me 1 over -4 plus 3. In other words, 1 over -1. So I get a point that's to the left of the vertical asymptote and below the horizontal asymptote. So I'll just draw something that always has that property. This section has numerous applications, and we look at one of those to finish things up. So a company that manufactures running shoes has a fixed monthly cost of $300,000. It costs $30 to produce each pair of shoes. In A, we write the cost function C of producing X pairs of shoes. So writing the cost function isn't too bad. You have this fixed monthly cost of $300,000, no matter how many pairs of shoes you make. And it's $30 for each pair. So that's $30 times however many pairs of shoes you make. In B, you want to find what's called the average cost function. So when you want to find an average, like say I want to find an average quiz score or something, I add up all the quiz scores and divide it by the number of quizzes. It's the same principle with average cost. Take the total cost divided by the number of pairs of shoes you've produced. The total cost is what we found in part A, 300,000 plus 30x. This is to produce X pairs of shoes. In C, we're asked to find and interpret C bar of 1,000, C bar of 10,000, C bar of 100,000. So for example, if we did C bar of 1,000, that would be 300,000 plus 30 times 1,000 over 1,000. And if we simplify that, we get 330. The meaning of this is 1,000 pairs produced equates to $330 per pair. So on average, the cost per pair for a pair of shoes to produce a pair of shoes, if you produce 1,000, is $330 for each pair. We could find C bar of 10,000. In other words, what is the average cost per pair if we produce 10,000 pairs? So that's 300,000 plus 30 times 10,000 over 10,000. If we work that out, we get 60. So if we produce 10,000 pairs of shoes, this averages out to $60 per pair, like the cost to the producer averages out to $60 per pair. If we do C bar of 100,000, so that's 300,000 plus 30 times 100,000 all over 100,000. If we simplify this, we get 33. And so what this means is that if we produce 100,000 pairs of shoes, the average cost per pair is $33. So we see that that average cost per pair is dropping. In D, what we're asked is, what is the horizontal asymptote for the graph of the average cost function C bar? And we'll describe what this means. Horizontal asymptotes are found like in this case, where we have the degree on top is the same as the degree on bottom, which we have here, x to the first and x to the first, is found by dividing the leading numbers. Leading doesn't necessarily mean the farthest term to the left. It just means the number in front of the highest power of x. If we divide these numbers, well, that's 30 over 1 or 30, excuse me. The meaning of this is that, well, we can see what's happening as the number of pairs goes up, the average cost is going down. This tells us that specifically it's going down toward $30. So as number of pairs increases, average cost approaches $30. So that's the meaning here. We're never going to actually reach $30. It'll always be $30 and some change, but it's getting closer and closer the more we produce. Okay. Okay, so that's the end of the handout for 2.6. We'll also look at the handout for 2.7. I'm going to plug in my computer real quick. 1 second, it's about to die. Okay. Okay, so in 2.7, we talk about what are called polynomial and rational inequalities. I've got, various steps here for solving these, but we'll of course see them in the examples. So polynomials, remember, those are nice powers of x. You add and subtract only positive integer like x to the squared, x to the third, x to the fourth. You only add and subtract those nice powers of x. So when we want to solve a polynomial inequality, say like example 1, the steps to do so are, at least at first, similar to solving polynomial equations. So like if I want to solve x squared minus x is greater than 20, in fact, the first thing I'm going to do is solve the equation x squared minus x equals 20. So I'm going to start in sort of a familiar way. So typically when we see this, we like to bring everything over to one side and hopefully it factors. In this case it does. 4 and negative 5 would multiply to negative 20, but also add to negative 1. So the solutions of this equation are negative 4 and 5. But we have to be careful to understand this is an inequality, not an equation. Negative 4 and 5 make the equation, or make this an equation, not an inequality, but they're not useless. So what we do here to figure out the actual solution set is we put these numbers on a number line. So negative 4 and 5. I'm going to pick some sample points in each region. Any number will do. So something to the left of negative 4, something in between these two, and something to the right of 5. And we're going to put these numbers in the original inequality. X squared minus x is greater than 20. These are the only places where it's an equality. So if I plug in negative 5 to the inequality and it's true, then it's going to be true everywhere until negative 4, when perhaps it switches to be from being true to false or vice versa. It may not switch, but we're going to find out. So let's put in negative 5 to the original inequality. So that's negative 5 squared minus negative 5 greater than 20. This says 25 plus 5, so that's 30, is greater than 20, and that is, of course, a true statement. So what I can do here, just to remind myself, is I'll write a little t here. Okay. Now let's check our representative number between negative 4 and 5. We put 0. So that would ask, is 0 squared minus 0 greater than 20? Well, then that would say 0 is greater than 20, which is, of course, false. We can indicate this to ourselves on our number line by writing a little f here for false. Finally, we plug in x equals 6. So that's 6 squared minus 6 is greater than 20. In other words, 36 minus 6, or 30, is greater than 20. And this is, of course, a true statement. So our letter here is going to be t. And now we can see the solution set of the inequality. It's true for all numbers before negative 4 and true for all numbers after 5. So the way we write the solution set, negative infinity to negative 4, union 5 to infinity. We need parentheses on the negative 4 and the 5 because this is a strict inequality. It doesn't say or equal to. Okay. So the way we graph this on the number line, that's the other thing that's asked for us on MATLAB. Well, you have all the numbers left of negative 4 and all the numbers right of 5. Okay, let's do another example. So here we're going to solve and graph the solution set of this on the number line, 2x squared less than or equal to negative 6x minus 1. Again, let's start by solving an equation. 2x squared equals negative 6x minus 1. Well, we'll bring everything over. So that's 2x squared plus 6x plus 1 equals 0. This one's not going to factor though. Like if I imagine just off to the side here, the only way that it could possibly factor is like this. I need 1 times 1 to get the 1 on the end, 2x times x to get the 2x squared, and all the signs are positive. But if I do a FOIL of this, it's not going to be 2x squared plus 6x plus 1. So it's not going to factor. Then we're going to need the quadratic formula. with a equals 2, b equals 6, c equals 1. So x is negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's negative 6 plus or minus the square root of 6 squared minus 4 times 2 times 1 all over 2 times 2. So that's negative 6 plus or minus the square root of 28 all over 4. Now 28 can be written as 4 times 7. And the square root of 4 is 2. So we have x is negative 6 plus or minus 2 times the square root of 7 all over 4. Well, you can take a 2 out of all of these. So I'm at negative 3 plus or minus 1 times the square root of 7 all over 2. So here, these are the zeros. These are the solutions of the equation. What I'll do then is I'll put these numbers on the number line. And since these aren't, like very intuitive numbers, it might be helpful for us to get an approximation of them to see what's a number I can pick to the left, one in the middle, and one on the right. This one's about negative 2.8. And this one's about negative 0.18. So I could pick like negative 3, that would be to the left. 0, or not 0, negative 1 would be in the middle of these two. And 0 would be a number to the right of the upper solution. And so what we're going to do with these sample numbers is we're going to put them in the original inequality. So we're going to put these in the inequality 2x squared is less than or equal to negative 6x minus 1. So let's check these three numbers. Let's use negative 3 first. So 2 times negative 3 squared less than or equal to negative 6 times negative 3 minus 1. That says 2 times 9, which is 18, is less than or equal to 18 minus 1, or 17, which is certainly false. So I can put a little f over here if I wish. Next, we're going to put in negative 1. So that's 2 times negative 1 squared less than or equal to negative 6 times negative 1 minus 1. 2 times 1 is 2. Here's 6 minus 1, that's 5. And so that is a true statement. So I'll put a little t for true here. Next, I'll put in my 0. So that's 2 times 0 squared less than or equal to negative 6 times 0 minus 1. 2 times 0 is 0. Here is 0 minus 1. 0 is not less than or equal to negative 1. That is, this is false. So I'll put a little f here for false. So we see that the one interval on which this inequality is true is between the roots of the equation. So my solution set then, bracket, because of the or equal to, -3 minus square root 7 over 2 to -3 plus square root 7 over 2. And we could make this on the number line by sketching brackets at the endpoints of the solution set and just shading in between them. Okay. Excuse me. So in the third example, we're going to solve and graph the solution set on a real number line here. X cubed plus 3x squared less than or equal to x plus 3. Again, let's solve an equation first. So that's x cubed plus 3x squared equals x plus 3. As usual, we'll get everything over to one side. So that's x cubed plus 3x squared minus x minus 3 equals 0. We can try to factor this by grouping. It has 4 terms, so it makes sense to try that. We can factor out an x squared from the first group, leaving us with x plus 3. You could factor a -1 from the second group, again leaving you with x plus 3. You now have a common factor of x plus 3. And when we factor that out, it leaves us with x squared minus 1. Now, x squared minus 1 factors further as x minus 1 times x plus 1. So the roots of this equation then are -3, 1, and -1. Let's put these on the number line, pick some numbers between and beyond them, and see where the inequality is true. So to the left of -3, I could pick -4. In between -3 and -1, I could pick -2. In between -1 and 1, I could pick 0. And beyond 1, I could pick 2. And we're going to put these in the original inequality. Okay. So let's put in -4. So that's -4 cubed plus 3 times -4 squared less than or equal to -4 plus 3. So this would say that what, -64 plus 48, so -16 less than or equal to -1. And that is a true statement. So I'll put a little t here. Next, we put in -2. So -2 cubed plus 3 times -2 squared less than or equal to -2 plus 3. So that's -8 plus 12, 3 times 4. So that's 4 less than or equal to 1, which is of course false. Next, we put in 0. 0 cubed plus 3 times 0 squared less than or equal to 0 plus 3. Left side then is 0. Right side is 3. So that's a true statement. Sorry, I forgot to write false here. So this one is true. So I'll write a little true between -1 and 1. And finally, we plug in 2. So that's 2 cubed plus 3 times 2 squared less than or equal to 2 plus 3. That's 8 plus 12, because that's 3 times 4. So that's 20 less than or equal to 5. So that's, of course, false. So we have a true statement before -3 and between -1 and 1. Since we have an or equal to on our inequality, we'll use brackets. So that's -infinity to -3 union -1 to 1. On the number line, so we just put all the numbers left to -3. And then from -1 to 1, we shade. Okay. So going on to the next example. In example 4, we're going to solve, and so now we're looking at what's called a rational inequality. So a rational inequality is where we have a fraction function instead of just a polynomial. And we can see this in example 4. In principle, we're going to solve it the same way as we did before. We're going to start by solving an equation, put the solutions on the number line, but fractions have this extra issue that you don't want the denominator to be 0. So we're going to have to watch out for that as well. So let's solve the equation 2x over x plus 1 equals 1. Now, we can't solve for x if it's in the denominator of a fraction. So let's multiply both sides by x plus 1. Here, x plus 1s would cancel, leaving us with 2x. And of course, x plus 1 times 1 is just x plus 1. Two x minus x is 1x. And of course, we're left with 1 on the right side. But we have to be careful here because if we just put 1 on the number line, now somebody could correctly say, okay, let's choose a number to the right, we'll pick 2. But then that person could come along and say, let's pick a number to the left of 1, that's -1. The problem with -1, it makes the denominator 0. So we can't use that number. What we do then is we're going to mark it off on the number line so that we can choose around it. Okay. So the -1 is here because it makes the denominator 0. So I'll say we want to avoid this number. So we can pick something to the left of -1 like -2, something between -1 and 1 like 0. So let's put these numbers in the inequality 2x over x plus 1 is greater than or equal to 1? Okay, so let's use -2. So that's 2 times -2 over -2 plus 1 greater than or equal to 1. So I have -4 over -1. So that would say then that 4 is greater than or equal to 1, which is of course a true statement. So I'll put a little t here for true before -1. Next we pick 0. 2 times 0 over 0 plus 1 greater than or equal to 1. Well, that's 0 over 1, and we're saying 0 is greater than or equal to 1. That is a false statement. Finally, if we put in 2, so that's 2 times 2 over 2 plus 1 greater than or equal to 1, which gives us 4/3 is greater than or equal to 1. And that is true. 3/3 is 1, so 4/3 is bigger than 1. Now, when I write the solution set, I have to be a little careful. There is an or equal to, but I say that I have to have a parenthesis on the -1. The reason for this is because -1 makes the denominator 0. So I can't plug it in. It's just a boundary. Okay. So let's note there's a parenthesis on -1 because it makes the denominator 0. You couldn't possibly include it in the solution set because you can't even plug it in. And then we can graph this on the number line as well, something like this. The last thing we look at on this handout is an application of inequalities. In example 5, it says an object is propelled straight up from ground level with an initial velocity of 80 feet per second. Its height at time t is modeled by s of t equals -16t squared plus 80t, where the height s of t is measured in feet and the time t is measured in seconds. So in other words, if you want to know the height of the object that's been propelled, you would simply plug in t, the number of seconds since it was propelled. Sorry, plug in t to this function, and the number will be that you get from that will be the height of the object at that time. So we want to know in which time interval will the object be more than 64 feet above the ground. In other words, we wish to solve s of t is greater than 64. Or you could say -16t squared plus 80t is greater than 64. Well, we're going to approach this the way we've approached all the other ones. Let's solve an equation. So that's -16t squared plus 80t equals 64. We could say then this is -16t squared plus 80t minus 64 equals 0. Now, this can factor. First of all, you could take a -16 out of everything, leaving us with t squared minus 5t plus 4. Now, that expression itself factors as t minus 1 times t minus 4. So the zeros here would be t equals 1 or t equals 4. And so now what we'll do is we'll put those numbers on the number line and choose numbers around them to plug in the inequality to see where we get something that's true or false. So we're going to put these in negative 16t squared plus 80t is greater than 64. If we use 0, we have negative 16 times 0 squared plus 80 times 0 is greater than 64. So 0 is greater than 64, and that is, of course, false. If we plug in 2, that would say negative 16 times 2 squared plus 80 times 2 is greater than 64. In other words, 96 is greater than 64, and that is, of course, true. Finally, we plug in 5. So that's negative 16 times 5 squared plus 80 times 5, greater than 64. But that would say 0 is greater than 64, which is, of course, false. So the time interval on which the object is higher than 64 feet is between 1 second and 4 seconds, giving us this interval. Okay, so that's it for the 2.6, 2.7 handouts. Thanks for watching.